Good morning. Today we are going to have a discussion on multi-level indexes. We already discussed single level indices, and now we are going to have multi-level indexes. For example, suppose that in a book you have say different types of four portions are there, and suppose that for each portion there is a separate index. Then this is just like my multi-level index. That means index 1. So in the front as in the face page or in the opening index you have say 5 different topics are there in the book. Then index of that 5 topics will be there in the first page, and when you go to that particular portion, then in that you can have a different index. That means that is the next level of index. Just like that, here, because a single level index is an ordered file, we can create a primary index to the index itself. That means index of index can be created. Actually, index is an ordered file, and index to that index can be created. In this case, the original index file is called the first level index, and the index is called second level index. We can repeat the process. That means we can have this up to any level. That means third level, fourth level, etc., up to the top level, until all entries of the top level fit in one disk block. Okay. Now, multi-level index can be created for any type of first level index, whether it is primary, secondary, or clustering index, as long as the first level index consists of more than one disk block. See here, this is an example of a 2-level primary index. Here in the first level, that means initially here you can see here you can see that this is the second level index. Primary level you have 2, 8, 15, 24 means 2 is pointing to the record 2, and in that we have another record which is having primary key field of 8. That means 2 to 7. That means 8 is there in the next block, 15 is there in the next block, 15 is there in the next block, and 24 is there in the next block. Then 2 to 7. 2 to 7 will be there in the first block, and 8 to 14 will be there in the second block, and 15 to 23 will be there in the third block, and 24 and 29. That means that is in the first level you have 2, 8, 15 and 24. It is a separate block. That means this first base level, the 2, 8, 40, 15 and 24, that forms a block. Thus the next block is 35, 39, 44 and 51. That means 35 to 38, 39 to 45, 44 to 50, then 51 to 54. Just like that. That means that is the first level index, and index of that index is in the second level or top level. That means here you have, that means here in the leftmost index or second level or top level index you have 2 to 35. 2 to 34 you have to go to the first block. Then 35 to 54 you have to go to the second block, and 55 to 84 you have to go to the third block, and if it is above 85, greater than or equal to 85, you have to go to the next block. And this is this is an example of a 2-level primary index. The main difficulty with this is insertion and deletion of data is very difficult. Insertion and deletion of data is very difficult as far as 2-level primary index is concerned. Such a multi-level index is a form of search tree. It is just like a search tree. Have you heard of binary search tree? Binary search tree means you have a node, you have a root, and in that root you have a key, and the left subtree is having all the nodes which is less than or equal to the value of the current root node, and on the right you have all the elements which are greater than or equal to the root node. And just like that, if you take any node, if it is a binary search tree, the left subtree is having less than or equal to the current node, and for in the right subtree every node is having a value which is greater than or equal to the current node. So like that, here in a multi-level index, it is a form of search tree. However, insertion and deletion of new index entries is a severe problem because every level of the index is an ordered file. So every level, see here, every level should be an ordered file. See, in the second level you have 235, 55 and 85. These are all, this is ordered. Then the first log we have 2, 8, 15 and 24. 35, 39, 44, 51, 55, 63, 71 and 80. All these are ordered. That means here we see the key field also. This is the actual data file. You have 2, 5, 8, 12, etc. 15, 21, 24, 29. That means indexing is possible. Two-level indexing is possible only for an ordered file, and in this insertion and deletion of data is a very difficult task. So that's all about multi-level indexes and a node in a search tree with pointers to subtrees below it. See here, this is a node. This is a node. Suppose that here P1, K1, P2, K2, etc. Ki minus 1, Ki minus 1, Pk, Pi minus 1, Pi, P1, K1, P2, K2, etc. Ki minus 1, Pi minus 1, Ki. It is not K1, Ki, then etc. Kq minus 1, PQ minus 1, etc. So that means here this is a block in which you have q minus 1 number of keys. This is a block which has q minus 1 number of keys. Q minus 1 number of keys. Okay. Then the keys are K1, K2, K3, etc. up to KQ minus 1. So a total of q minus 1 keys are there. Q minus 1 keys are there. That means here P1 is pointing to a tree in which every node is having key value which is less than K1. So here you have P1 and here you have K1. Then P1 is the P1 is pointing to a subtree, and in that subtree every element of that, every element means, suppose that you have a key value here, that means this is a subtree, and in that subtree every key value should be less than K1. And likewise, suppose that here we have a pointer in between Ki minus 1 and Ki. This is not K1 actually this is Ki. In between Ki minus 1 and Ki, it is pointing to a subtree, and in that subtree every key value should be in between Ki minus 1 and Ki. Every value in this subtree should be in between Ki minus 1 and Ki. And the last one is Kq minus 1, and here we should write Pq minus 1. It is not P1, it is P I minus 1, and in that is the rightmost pointer, and that pointer is pointing to a subtree in which every key value in that subtree should be greater than, every key value should be greater than Qk minus 1. X should be greater than Kq minus 1. So this is a search tree. That means suppose that you are going to search for a particular record in this. That means by when we are processing this first block, then you can find out the actual search tree in which you have to search for. Then go to that subtree, and then you can easily reach your actual destination. Okay. So this is a search tree of order p is equal to 3. P is equal to 3 means every node is having a 3 number of pointers and 2 key values. 2 key values, that means p number of pointers and p minus 1 number of keys. So this dot is representing a 3 node pointer, and if a dot is not there, that means it is a null pointer. That means here you can see that in the root node you have 5, and 5 has a left subtree, and in that left subtree all the values, that means 5 left to that 5 you have a subtree, and in that subtree you have 2 blocks, and you have 2 values 3 and 1, and you go to the right, then all the values are greater than 5, that means 6, 9, 7, 8, 12. Okay, see, you come to this node where the data value is 3, that is having a left subtree, and that left subtree is having a key value 1, that means that is less than 3. Go to the right, that means in a node and immediately after that 5, that is pointing to a node which is having 2 k values 6 and 9. So in between that 6 and 9, it is pointing to another node in which you have 7 and 8. Those 7 and 8 are in between 6 and 9. So immediately to the right of that 9, you have another subtree in which you have a value, you have a key which is 12, which is greater than 9. So this is actually a search tree of order 3. P is equal to 3 means number of pointers are 3 and number of key values for each node is 2. Okay. Now dynamic multi-level indexes using B trees and B plus trees. Most multi-level indexes use B tree or B plus tree. That means implementation of multi-level index can be done using B tree or B plus tree. So actually in our secondary storage device and in our actual implementation, we are using B trees and B plus trees for storing data value. Most multi-level index use B tree and B plus tree data structures because of the insertion and deletion problem. In this case, insertion and deletion is very easy. So those algorithms, our point of discussion is not considering the insertion and deletion of. So you need only study the basic structures of B trees and B plus trees, and your data structures you might have studied. I think you studied B trees and B plus trees in your data structures class. There insertion and deletion of B trees and data in B trees and B plus trees you might have studied. Okay, these data structures are variations of search trees that allow efficient insertion and deletion of new search values. In B tree and B plus tree data structures, each node corresponds to a disk block. That means actually in our previous class we discussed what is a block, and example that means in your secondary storage device, data is recorded in the form of tracks, and tracks are divided into sectors, and each sector is carrying a block, and suppose that the actual sector size is say 512 bytes, then 512 bytes is used for storing one block. One block means in one block you can have many records, and that those things we already discussed. Each node is kept between half full and completely full. That means if you need to store, or if you have to allocate a new block, at least it should be half full. Okay, that means either it is half full or completely full. Suppose that if it is not half full, then some other adjustment you have to do. That I think you studied that in the data structures class. Now An insertion into a node that is not full is quite efficient. An insertion into a node that is not full, you can easily insert that element to that node. If a node is full, then again if you want to insert, then you have to allocate some other block and you have to make those adjustments. Splitting may propagate to any to other levels. That means suppose that in a block we can occupy only 2 records, and suppose that if you want to insert a third record, what will happen? A new block has to be allocated and the your pointers and all has to be adjusted. Okay. Splitting may propagate to other tree levels. Deletion is quite efficient if a node does not become less than half full. Deletion is quite efficient. That means after deletion of a particular node, if it becomes less than half full, then again you have to make some other arrangements. That means one of the condition is every block should be at least half full. Okay. If a deletion causes a node to become less than half full, it must be merged with the neighboring nodes. These algorithms you have to study, but in our syllabus it is not given. That means you need only study the structures, and algorithms are not required. Okay. Then difference between B tree and B plus tree. In a B tree, pointers to data records existed all levels of the tree. In a B plus tree, all pointers to data records exist at the leaf nodes. That means in a B tree, data is stored in every node, whether it is in the first level, whether it is a second level or third level. Every node is at all levels that data is stored. But in a B plus tree, only indexes are stored in the base levels, and the actual data is stored in the leaf nodes only. A B plus tree can have less levels compared to the B tree. Okay. Then this is a B tree structure. Here, see, here P1, K1, PR1, P2, etc. K I minus 1, PR I minus 1, PI, Ki PRI, and KQ minus 1, PR minus 1, PQ. The meaning is here P1 is a pointer to a subtree, P2 is another pointer to a subtree, and this K1 PR1 which lies in between pointers P1 and P2. The meaning is the key value in between those two pointers is key value in between these two pointers P1 and P2 is K1, and K1 is actually it's a primary key value. It's a primary key value, and the data corresponding to that primary key value has to be kept somewhere, and pointer to that record, that is PR1. That is PR1. Okay. Likewise, Ki minus 1, PR I minus 1. The meaning is if you have a data value, or if you have a key value Ki minus 1, and the record corresponding to this Ki minus 1 has to be kept in a particular block, and that address is PRI minus 1. What about Ki and Pi? The data value corresponding, the actual record corresponding to the key value Ki is stored somewhere, and PRI is a pointer to that, and like that. Okay. See here. See, 5 and 8 are the key values in the second level, and the leaf nodes you have 1, 3, 6, 7, 9 and 12. This is an example of a B tree. Now 5 and 8 are the key values in the 0th level. Then 5 is pointing to a record, and that is the second box. 5 in the first box and 0 pointed in the second box. Then that is pointed to the actual data record corresponding to 5 is pointed to by this one. Okay. Then 8 is also pointing to some other data record, and now left to that 5 you have a pointer to a block, and in that you have two key values 1 and 3, and in between that 5 and 8 you have another pointer which is pointing to 6 and 7, and whatever is in between 5 and 8 that has to be kept there, and if the key value is greater than 8 that has to be kept on the right subtree. So this is very easy to understand. So this is the basic B tree data structure, and in the case of B plus tree, internal node of a B plus tree with Q minus 1 search values. The search values are K1, K etc. K minus 1, K etc. Q minus 1. Here Q minus 1 key values and Q pointers are there. If you have set 10 key values, then definitely 11 pointers are there. Leaf nodes of a B plus tree with Q minus 1 search values and Q minus 1 data pointers. Q minus 1 search values and actually we have Q number of pointers. Here it is written like Q minus 1 data point, that is wrong, and Q data pointers are there. Now P1 is pointing to a subtree which is having key values which is less than K1 and K minus 1 K. This is just like our B tree, and one thing is in B tree, go to B tree. In B tree, this 5 and 8 are stored here, and pointer to the data record which is keeping that pointing to this is 5 and 8, and the actual record which is pointed to by this 5, we can reach that from this level itself. But in the case of B plus tree, you are actually storing this you are going to store only the key value here 5, and in the leaf node also you have this 5. Here it is 8, in the leaf node also you have the value 8, and there you are going to have the pointer to the data, pointer to the actual record stored. So that is the difference between B3 and B plus tree. That means in B plus tree, the actual data value is pointed to by only the leaf nodes. That means all other nodes which are not leaves, they are only for redirecting, only for searching purpose, and the actual data value can be accessed only from the leaf nodes. You cannot access that from the internal nodes. Okay, so that is the difference between B tree and B plus tree. That is the nodes of a B plus tree. Insertion and deletion of data in a B tree and B plus tree is very, you have to study that in your algorithms class. So you have to go through that, and at this point in time, as far as database is concerned, you need to study only the basic structure. So this is the way we are going to have multi-level indices. That means multi-level indices are implemented using either B tree or B plus tree. Okay.